Let me check if it started. Yes. Now let me share again my screen. And so we have about 45 minutes to go. And let me see if it works. Yes, I wanted. Okay, very good. I also checked the translation of wrecked because indeed it's a good term that you used to mean that they are destroyed. Okay. Now, there is in this web page that is dealing with climate change and impact on the water cycle, including seas. There are other sections looking at, let me go back, at changes in rainfall, other than sea level, I mean, other kind of changes in rainfall, and changes in, so here it's rainfall, precipitation. So changes detected and predicted in precipitation, okay? And you may know that it's often proposed by the media that climate change is going to increase extreme precipitation and decrease the average precipitation. So here there is a discussion on that. And then there is a discussion on flood and droughts. So there is sea level, we dealt with. Let me go down. Flood and droughts. Okay, so floods first and then droughts. So I go down. Okay, let me just stop here in droughts, because droughts are something that we can relate to ocean engineering. Now, what is the take-home message? I just want to give a brief summary. You may want to read these sections in detail by taking into account, once again, that I will not ask at the exam any question related to this lecture. So in particular, I will not ask any question related to the effect of climate change on floods and droughts. But you may be interested in knowing more, and then you may read them. The take-home message that I would like to summarize without going into the details is that, again, like for sea level rise, like for temperature, there is uncertainty, but the uncertainty in the prediction of future floods and droughts is much higher than the uncertainty of the predictions for temperature and sea level rise. Because we are talking again of processes, rainfall, floods, droughts, that are characterized by striking heterogeneity, and processes which are also rapidly varying in time. If you think about rainfall changes in time very rapidly, more than the sea level, more than temperature. And so the ability of climate models to reproduce floods and droughts, it's really limited. And this is the take-home message that I wanted to give you, because it is extremely important to take into account that when you go to technical design, when you deal with technical design in the presence of climate change, and you deal with something related to floods and droughts, you have to be very careful, and particularly very careful about predictions, reliability of predictions. Droughts in particular, they are an increasing reason of concern today, because they are impacting the society at a relevant rate, at a relevant level. And the reason is, of course, related to the management of water resources for both civil use and irrigation. Droughts also are particularly problematic because climate models are not able to reproduce their persistence, meaning that droughts, when they occur, they may last for a long time. This is what our experience, our analysis of historical data suggests. Drought may last indeed for a long time, several years. And I can give you some examples related to that, like the Millennium Drought in Australia. You see it's linked here in this in my web page. And this is a drought that lasted 10 years and then reverted back. Now it's declared close. And it was really an impressive event because of the long duration. And here in this webpage, you can find also some details on the climatic condition. And it is believed that one of the causes of these extreme events is the fluctuation of El Nino. I'm sure that you heard about El Nino, and indeed, this is a phenomenon that climate models do not reproduce. What is El Nino? El Nino, there is a figure here which is enlightening. It's a naturally occurring weather pattern. So there is no clear indication that El Nino is influenced by global warming. And it's a weather pattern which is triggered by a periodic variation of sea surface temperatures over the tropical Eastern Pacific Ocean. Let me give you this, let me show you this figure. And this is in particular showing a La Nina phase, but what is important to highlight here, La Nina is a phenomenon that it's originated by a temperature difference in the ocean like El Nino with the opposite side sign, meaning that here you see the Pacific Ocean with the east on the right and the west on the left. So when you have warm temperature at the surface in the west and cool in the east, then this is called La Nina. When there is the opposite situation, it's called El Nino. So La Nina, you see that the effect of this change in the temperature, and the change in the temperature, you know, it's originated by weather conditions. So when you have conditions originating this difference in temperature into the ocean, what you obtain is a circulation of water in the ocean that determines, by bringing the cool water on the left, determines wet conditions with low atmospheric pressure on the left, on the west, and determines high pressure and dry condition on the east. And in this case, La Nina is originating rainfall on the west, and meaning on the west of the Pacific Ocean, and in particular Australia, and it's originating dry conditions on the east of the Pacific Ocean in the United States. This is La Nina. When you have El Nino, it's the opposite circulation, which brings dry conditions in Australia and wet over the United States. This particular imbalance of temperature may last for several years, because once that the imbalance is triggered, then it's persistent. And the reasons why it's triggered are not fully understood. But it looks like, as I said, the global warming is not affecting the frequency of these events. The fact is that when this anomalous circulation pattern starts, then we enter into a El Nino phase, they can last for a long time. And so this is something that it's really relevant to determine these droughts that last for a long time. And again, it's not clear whether these are phenomena that are caused by global warming. What is important to take into account is that these phenomena are not reproduced by climate models, because given that we don't know the genesis, we don't know how these phenomena are generated, of course we cannot reproduce them into a model. And therefore the result is that if you rely on a model simulation of future climate, you may underestimate the risks of droughts. This is the take-home message of this explanation. I just want you to be fully aware that you may run the risk of underestimating some hazards if you blindly rely on a prediction by climate models. So in this case, if we are particularly concerned about droughts, we have to use a different prediction method, or let's say we have to integrate the prediction by climate models with an additional information. And this is the take-home message that I wanted to convey to you, because there is in some way the convincement that climate models are conservative. They may be conservative, but not in any condition and not for any risk. So we cannot use a universal model to make a climatic prediction. We have to basically use a model that is tailored to our target. Okay, now let's move forward so to another consideration, and I scroll down. And the consideration is, so what? So what should we do in order to make a technical design of in the presence of climate change? Okay, let me say that there are two types of actions, and this is an important message that I would like to convey to you, that you have to get informed of, related to resolving the problems of climate change. Two types, two categories of actions. The first one, look at the screen, is mitigation. And the second one is adaptation. Don't confuse them. Beware of the difference. What is mitigation? As the term suggests, climate change mitigation is a set of actions that reduce climate change. Okay, like reducing CO2 emissions. This is expected to reduce the human component of climate change. I think it is clear. On the other hand, the second category, adaptation, means that you don't reduce climate change, but get used to it. So basically, you don't mitigate the effect, you mitigate the consequences. And it's important to distinguish between the two. Keep in mind that there is also quite a vivid discussion in the literature about the priority of one category with respect to the other one. Because on the one hand, there are climate scientists who really push for mitigation, because climate scientists are concerned by climate change, human-induced climate change, and then they want to resolve completely the problem. Adaptation looks to them like a lower level solution, okay? On the other hand, there are the engineers who generally are more convinced by adaptation, because it's a more effective solution. Engineers want to solve the problems in a reasonable time frame. Mitigation takes a long time. We all know that we are all told that even if we started now reducing the emissions, it will take tens of years before you see the effects. And engineers are often called to provide a quick solution to a problem, so engineers are more in favor of adaptation. Of course, these are two different actions, and adaptation for Harbour engineering is building coastal protections, is sand bypass systems if there are changes in the wave dynamics that cause problems related to erosion and siltation. And adaptation is to protect the structures and the coasts in some way. And mitigation is something that has to deal with a different spatial scale. It's global, needs to be global, and therefore it needs also an interaction with a different political level. Now, what if we are called to design a climate change adaptation structure? Because this is the relevant issue. So we engineers, the relevant issue for us, we engineers are called usually to intervene with climate change adaptation. And we are given little technical guidelines, as I said, to design under climate change. So how should we move forward? Okay, before looking at what is specified in the lecture, which you can also read by yourself, I want to provide you, show you a figure related to the so-called bottom-up approach. Okay, let me just, there is a link. The link is related to another one of my lectures. Let me show you a picture because I want to make the concept clear. So the question is, how should we design structures, protection structures in the face of, in the presence of climate change? Now, let me just go to the picture, sorry. I think this is good, but on the other hand, I would like to, okay. I have also a better figure, but let me focus on this. Sorry if I'm scrolling very rapidly. Okay, let me just focus on this picture. And let's focus on the right part of it, the bottom-up approach. So again, the question is, I am in the presence of climate change, how can I take it into account when designing a groin, a breakwater, for instance? And we are engineers, we need a very pragmatic approach. So there is a consistent literature suggesting that we can use climate scenarios. And climate scenarios, look at the left, top down, basically starts from the prediction of climate. And then this refers to rainfall, but to floods. But let's imagine how this figure could become in the top-down approach, left column, with respect to our problem, Harbour engineering, design of a breakwater. So you have a predicted climate, which means, in this case, predicted wave heights. And then you use, or the predicted climate may be in terms of wind. And then you use a transformation model to estimate the wave height generated by wind after climate change. And then, basing on this simulation, this modeling cascade, you design your structure. This is one possible approach, and there is a consistent part of the literature suggesting it. But this is a literature that usually is not referred to engineering. Let's now go on the right. And let's refer to the engineering literature. In the engineering literature suggests that, first of all, you have to refer to the classical methods of engineering. And what do these methods suggest to you? To look at data and quantify the problem with data, not with models. Okay, and the models are useful when you don't have the data, but when there are data, the suggestion of classical engineering is estimate your wave height by using observations, okay? And then you get an estimate of the hazards in the current situation. So it's called bottom up, because it starts from the assessment of the current situation and check if there are problems. Usually they are, because when you are called to design a climate change adaptation structure, usually you are in a situation such that you already have a problem. If there are no problems, it's unlikely that you are called into play because some people predict that climate change will induce problems. Usually people they are concerned because something is going on already now. And therefore the recommendation is try to identify a solution, try to identify a structure and intervention that solves the current problem. Now, once that you use engineering, the classical methods, so you know how to design a breakwater, you know how to design a groin, just refer to your data and make the design. Once that you did it, then the question may come, what about climate change? And then the suggestion that I give to you, according to the bottom-up approach, is that you check the resilience of your intervention in the face of climate change. So you already designed a structure that it's a no-regret one because it solves a current problem. It solves a problem that needs to be solved already now. So it's a no-regret solution. Check if this no-regret solution is resilient. And then at this stage, you may take climate scenarios, climate models, and check what is the behavior, what is the performance of your solution with respect to the future climate. And here, you need to use all the information you have available, not only climate models, but also any expert knowledge you may have. And then you end up by identifying a solution, hopefully, that is a no-regret one and resilient. Because you may decide, after checking with climate models, that you need to heighten a little bit your breakwater. And so basically you may decide to add resilience if you have enough information to do so. And again, I stress you have to use all the available information in this phase. So this is the concept that I really would like that you keep as a take-home message. When you are uncertain about the future, start from the present and solve the present problems, because this leads to a no-regret solution. And then you may try to guess what the future will be to verify the reliability of the solution. Like, for instance, we talked about mangroves before, then you may identify a solution that makes use of mangroves to limit coastal erosion. And then you know that mangroves are, we were told by Martina that mangroves are in a way in front of an hurricane, maybe not, maybe break off, okay? And so the question would be, our climate predictions say that hurricanes are likely to increase or not. So the resilience of our mangrove solution is reduced by climate change or not. We make this check. And then it may happen that if you really trust that the frequency and magnitude of hurricanes may increase, it may be that you decide to, if for instance you coupled the mangroves with another intervention like breakwater, you may decide to increase the safety factor of the structure. I hope the concept is clear, and this is what underlines what should drive, in my opinion, your design activity in the presence of climate change. And then the lecture gives to you some guidelines, fundamental principles to be considered when designing an adaptation policy. And I think there is no need that we comment all of them. And because we already said that climate change vary by region, and also the effects may vary across demographic groups, this is true. And keep into account also the opportunities of climate change and try to use them. And also keep into account the costs. So full adaptation doesn't exist because otherwise it's too costly. If it would exist, probably it would cost too much. And I would say that the other ones don't need to be commented. And here you see a set of solutions, which refer to, in general, civil engineering. There are also some solutions for protecting the costs. I would say that here there is a section dedicated to design, more specifically. I think you can drop it at the current stage because it goes into the technicalities of how we can put together several different methods for generating future climatic scenarios. I hope that this lecture succeeded in giving to you an overview of what climate change is, how uncertain it is, and how pragmatic we should be when dealing with something that in general science poorly knows even today. And of course, this is an evolving subject, so it's important that you stay updated, and it's important that you also get that this is controversial, and the controversy is something that it's, it's something that you have to take into account in your communication. I would say that that's it for it, and it is our course in Harbour Engineering. And before I make a recap of what we did, I just would like to ask you if you have any question related to this lecture. Okay. Now, what I propose to do in about 15 minutes, it's to go through what we did and identify possible questions. Of course, I'm not providing a full overview, and I keep the recording open. So if your colleagues want to listen to this discussion, it will be possible. And as I said, the panorama of questions that I give to you now, it's not exhaustive, of course. It's not that I can only pick from these questions at the exam. They are just examples. And I think that what is the best way to illustrate these questions is to go quickly through the lectures that we had together. So we made a premise about the learning process. There is nothing that I can ask at the exam about this. Okay, so just let me go slower. And the learning process adopted in the course. It was the first lecture. There is nothing that I can ask. Okay, so let's go back. And then there is a premise on cost management and beach design. So here, there is something that I may ask related to terminology. I think it was here, the link on terminology. I'm not sure whether it was in this lecture or the next one, probably the next one. But just keep in mind that I may ask some definitions, like, let me give an example. What is the definition that you give of coastline? What the definition that you give? What is the definition that you give of a swell? Even if it's something that I didn't teach myself, it may happen that I ask you basic definitions, and I have or what is a landlocked country? Okay, and I may ask you something like, in your opinion, how many landlocked countries we have in the world? Give me an order of magnitude. 1, 50, 100, 1,000, 10,000, and so the reply is 48, but it's just enough that you see some tens. This gives an idea of the fact that you are prepared on the basis of the subject. Okay, And or I may ask something even more detailed, like what is a wave amplitude, and just make sure that you can provide these basic definitions. A question that may look, it's a nice example. Sometimes I ask students, what is the specific weight of water? And they don't reply. And this is something that gives an example of why I ask these basic definitions, because I want to make sure that you reflected on what you studied, okay? And or I may ask, what is the specific weight of saline water? It's how much higher it is with respect to fresh water. And this is an example of definition and terms. Let me go through this lecture. I don't think that there is much more to say. I would say that all these discussions that we had, don't provide other food for questions. Now, let me move forward in the port planning and environmental impact. Now, let me see what's here. And, you know, I could ask you, what is a berth? Okay. And another thing that I may ask related to this lecture is a description of the loads, this figure. You don't need to be very, very detailed. You don't have to reproduce this figure, but mentioning, if I ask you what kind of loads a berth can be subjected to, a correct reply would be there are loads from the seaside, there are loads from the berth, and there are loads from the land side. And we can distinguish between vertical and horizontal forces. And then you may give some examples, like vertical loads are given by bollards, and also horizontal loads are given by bollards. And so these are the examples, an example of answer that would be considered correct. And then the combination of loads. So this is something that I may ask. How do you combine loads when designing a berth? Okay, and then another thing is the design life. I may ask you, what is the design life of a structure, of a berth structure, of flood protection works? And the information is here, okay? Breakwater 100 years, reinforced open berth structures 50, 100, and then rubber fenders 10 years. Just remember the order of magnitude. You don't need to remember the number precisely, but the order of magnitude is important. Okay, and then let me see the types of berth structures. Maybe that I ask you, what kind of berth structures do you know? Open solid structure, open structures, gravity wall structure, etc. And this is derived from here. And then the suggested dimensions. I think it is here. Yeah, suggested dimensions. So the order of magnitude of the suggested dimensions. And then I may ask also something like, what is causing the environmental impact of a port? And then you have to be able to, this would be a typical first question, descriptive. And you have to be able to provide a descriptive answer. I think that here it's okay. Now let's go back and next one. Next one is forcing estimation. So here there is, if I will remember, the link to the terms, nautical terms. Yeah, here they are. So I may ask, what is length between perpendicular? I may ask you, can you please sketch a ship and explain what is the beam, what is the draught, what is the freeboard, what is the length between perpendicular, etc. So try to pay attention to this box here. And then the windrows. The windrows is a typical question. So what is a windrows? How you estimate it? There is plenty of information, all the information that you require in this lecture. Another question is, what is probability? Because probability is an essential tool for you. And so what is a probability? What is a probability distribution? And then there is this formula, which I asked you to remember my memory. wind loads. And please remember it and be able to discuss it, okay? And then there is something later on related to the mooring lines. Okay, these terms, please try to have the picture clear. So you should know what is a forward spring, what is an aft spring, an aft breast line, etc. Okay, and what is return period? Okay, of course, we talked about design life first. Now, what is return period? And this part related to the return period studied in detail, okay? And also this explicit expression for the return period, this one, it's, please learn it, okay? Okay, now, wave forcing, don't remember by memory the formula, only for wind, okay? This one, not. Okay, that one, it's not necessary. But you should remember what are the effective, what are the independent variables in it, okay? So HS, D prime, the coefficients, try to, not to remember the formula, but try to remember the concept, okay? And then let's move forward. Groins. What's the difference between groins and breakwater? So provide me a definition. What is a groin? What is a breakwater? This is a very simple example of a very naive question that you should be able to fully address. Okay, and then groin design. There is the lambda rule here. The lambda rule, you should learn it. And also the typical dimensions. It's discussed, I think. Please try to remember this math here, how to compute the distance along the coast for groins. Typical dimensions, just try to remember these orders of magnitude. It's important. Okay, now let's go back. Next one. Stability, Shields criteria. Just please, this may be a typical question. Can you please tell me how the Shields criteria for the stability of our armor unit is derived? Okay, and if you can develop this mathematical proof to get to this final expression, this would be great. That would be great. And I think that's all. You may be required to explain how we can take into account of the slope in the Shields criteria, the slope of the sides of the groin. And it's not necessary that you remember this empirical relationship that you see here. And also the Hudson formula, it's not required. Okay, let's move to the next one. Sorry. Dredging. Here in dredging, there are some mathematics. There is some mathematics somewhere. And try to pay attention to mathematics. So this is a lecture that you should read with care. And similarity, this discussion to prove that you cannot reproduce both Froude and Reynolds numbers with a small scale model. Please, this is something that can be asked, okay? And then if you go down, there is another mathematics. Forget about this section, which was added by me later after the lecture. Okay, forget about this figure. but here there is further mathematics in the computation of the volumes of dredging, and in the computation of the volumes of water that are involved in the watering processes. And then I think that's it. Yeah, there is also these two conditions on the stability of water injection of the layer, of the boundary layer, in order to keep the turbidity close to the bottom. If you can please remember these two conditions. If you don't remember how to write the Richardson number, that's fine. I mean, don't learn this formula, but just remember the conditions on the numbers, okay? And I think for dredging, that's it. And for design of breakwaters, just remember the water setup. What is the water setup in the lee zone? I go forward here. Wave transmission, what is wave transmission? And it's not necessary that you learn these formulas. These are empirical formulas, but just learn what is wave transmission and what is water setup. Okay, don't learn this empirical relationship, but try to be able to answer to the question, what is wave transmission and wave setup? I would say that I am fine. Climate change is not a subject of any question. And I wonder whether you have something to ask me at this stage. No questions. Okay. Now, let me just say that, first of all, I would like to thank you because you were very patient with this unusual setting this year. And of course, your attendance was a bit, you are not many students. So I know that the numbers are a bit limited in your course. And I am pleased to say that I really appreciated the fact that I had a minimum number of students at any lecture, and a minimum means that a sufficient number of students. And I really appreciate the fact that today already 8 students compiled the survey. This is another confirmation that you paid attention to my lectures and to what I did. I am not sure I met your expectation in terms of excitement of the subject of my lectures. I'm not sure I met your expectations in terms of clarity. I am sure that for some of the lectures, I was maybe a bit too technical. On the other hand, I want to give you an education that is in a way that conforms to the education principle of engineering. We need to make sure that we have the knowledge of the theory and the knowledge of the technology, PC, programming, that allows us to solve the complex problem that the profession of engineer may present, may ask you to face. I try to do my best, but again, I'm not sure I met your expectation. And if you have any suggestion for me, and I really appreciate your feedback in the survey, if you did it, but also if you can always refer to me whenever you want. Again, if you believe that a Q&A session may be useful, you can take an agreement among the few of you who attend the lectures, and we can schedule whenever you want in May or whenever a Q&A session. I'm fully available. Okay, so let me share the screen so I can say goodbye for now. we are meeting again at the exam, and then we will have other opportunities, I'm sure, to meet, hopefully in physical presence next time. Any question? Last call? Let me look at the chat. Okay, thank you. Thank you once again, and see you at the exam, which you will find the dates on Alma Esami, let's say by tomorrow. Students, thanks, and let's keep in touch if you have any need. Ciao.
Thank you, Professor. Have a nice day.
You too.
Thank you.
You too, have a nice day.
you, Professor. Have a good day.
Thank you. Good day.
Thanks, Professor. Ciao.